Today we're going to talk about parametric equations and also how to derive them. For example 1, plot points to sketch the curve described by the parametric equations. Mark the orientation on the curve. Our interval is -3 to 2, so that will be our t values. Now we're going to plug in each of those t values into the x relationship and the y relationship to get our x, y coordinate points. For x, we have t squared minus 5, so I'll put in -3, square it, and then minus 5. Continue. The relationship between t and y is y equals t divided by 2, so do that for the y's. Let's go ahead and plot the points, starting with t equals -3. To mark the orientation on the curve, we started at this point for -3/2, and we continued over till we got to -1, 1. So the orientation would be going to the left until we reach -5, 0, and then we're going back to the right. For example 2, change the following to rectangular form by eliminating the parameter, then graph. Changing from parametric to rectangular, we often want to use the idea of solving systems of equations to get a relationship that is just between x and y. Because the x parameter only has one t, I'm going to solve for t in the x parameter. Now that we've solved for t, we can plug in 1 over x squared minus 1 for t in the y parameter. Notice the only possible values of t are greater than -1. Otherwise, we'd have to take the square root of a negative. Let's take a look at the x parameter. What can x be? No matter what, x cannot be 0. It's also not going to be any negative result, because once we square root t plus 1, we'll have a positive. So because t cannot equal -1 and x cannot equal any negative values, our domain must be x greater than 0. So if x must be greater than 0, let's graph 1 minus x squared with an x greater than 0. 1 minus x squared is an upside down parabola shifted up 1. Oh wait, it doesn't go less than 0, and at 0 we should have a hole. As t grows, the y value will get smaller and smaller, so our orientation is in this direction. For example 3, we're going to eliminate the parameter again and sketch the curve. Now I know a relationship between cosine and sine. That would be the Pythagorean identity, cosine squared theta plus sine squared theta equals 1. So let's solve for sine theta and substitute into our Pythagorean identity. What is that the equation of? It looks very similar to a circle, but since we have a denominator under the y squared, that's going to be a stretched circle, which is called an ellipse. The major axis, or the longest part, is going to happen on the y-axis because 9 is under y. We'll go up 3, down 3. Our minor axis is 1, or square root of 1, so 1 this way and 1 that way, and we can fill in our ellipse. To check the orientation of your curve, you can always plug in some values for theta, such as 0 and pi halves. And you can see that indeed we are moving counterclockwise. Even though equations are given in terms of a parameter, it is possible to find dy over dx and the second derivative of y with respect to x by differentiating and then dividing. Here are our formulas. If x equals cosine t and y equals 3 sine t, find dy dx and the second derivative of y with respect to x. First, I'll derive each of these with respect to t. Following our formula, we have 3 cosine t over negative sine t. Using trig identities, that is negative 3 cotangent t. Now it's time to derive our derivative. The derivative of negative 3 cotangent t with respect to t is positive 3 cosecant squared t. So to get our second derivative of y with respect to x, in the numerator we put 3 cosecant squared t. In the denominator we're going to put dx over dt. That is negative sine t. We can simplify that using trig ratios. And there's our second derivative. To find the slope and concavity, we're going to find the first and second derivatives. Start by deriving x with respect to t and y with respect to t. So let's find dy over dx. I'm going to derive the derivative of y with respect to x with respect to t so that I can get the numerator of the second derivative. To find our second derivative, we're going to put the derivative of the first derivative on top, divided by the derivative of x with respect to t. Which simplifies to be 3t. To find the slope at 2, 3, we need to know the t value, for which x is 2 and y is 3. As you can see, t equals 4. So to find the slope at the point 2, 3, we will evaluate dy over dx at t equals 4. To find the concavity, we'll make the second derivative equal to 0 and check the signs on either side. When t is negative, our second derivative is negative. When t is positive, our second derivative is positive. So our parametric equations are concave down when t is less than 0 and concave up when t is greater than 0. Write an equation of a tangent line to the curve defined by x equals t minus 1 and y equals 1 over t plus 1 at the point when t equals 1. Begin by deriving each with respect to t. This would make dy dx negative 1 over t squared divided by 1. If we evaluate that at t equals 1, we'll get a result of negative 1. When t is equal to 1, what are x and y? So when t is 1, our xy coordinate is 0, 2. And when the slope, evaluated at t equals 1, is negative 1, now I have a point and a slope for my tangent line. We've already learned an arc length formula for rectangular equations, but what about parametric? If a curve is smooth and does not intersect itself, the length of an arc is given by this integral. Using the parametric equations from example 6, find the arc length on the interval 1 to 3. Given that interval, we know a is going to be 1 and b is going to be 3, the limits of our integral. The variable used to describe arc length is usually s. From the previous problem, dx dt is 1. dy over dt is negative 1 over t squared. Oh, and we already know a and b, as I said before, are 1 and 3. Go ahead and use a calculator to get the value of this integral. And we get 2.1466, etc.